We will still talk about the hardware-software co-design receipt and still address opportunities and challenges from an hardware design perspective. So this is where we are in our roadmap. We were talking about how to compute, and we cover quite a lot of possible dedicated designs which we can do when we're talking about a feature-based flows. So using multiple cores which can be synchronized at the task level, using some degree of inexact processing so that we can deal with bit flips in memory without permanently crashing the system. And then we spoken about reconfigurable acceleration, especially something which is called coarse-grained reconfigurable arrays. And now we can compile the data flow graph of an intensive loop into a CGRA by using modulo scheduling. If you're interested in any of these topics, you can find references in the slides. I am around, so if you have any questions, I'm more than happy to address them. Then we turn the page and we look at opportunities for ML-based flows. And what I mentioned is that the best accelerator is no accelerator at all. And we have spoken about codebooks, and now we can use indexes to index tables storing floating point values, and now these indexes can be expressed with just a few bits. As I did this brief recap, hopefully everybody has arrived, and we can now continue in our roadmap. So what I mentioned is that when we have machine learning applications, these are very robust towards quantization. So we can express basically everything in terms of a handful of bits with negligible or very small impacts on the quality of service in terms of F1 score or in terms of accuracy. This is an opportunity, but is also a challenge if we want to have an hardware which can leverage this. If we have a general purpose processor, we don't have 3 bits or 4 bits arithmetic units which we can use in general. Plus, this type of robustness is very much layer dependent. So we would like to have a very flexible solution which allows us to change the representation of the data in terms of the number of bits in different layers. And what I'm going to cover today, which is called Bitline computing, is a type of processing which does exactly that. So Bitline computing is a type of compute memories. I'm pretty sure that I don't have to convince anybody that computing memories are promising, they are the future, and they have a lot of nice characteristics, including a massive parallelism which is built into the memory architectures, and the fact that memories are where the data is stored. So if we can do some computing locally, we may gain a lot of performance and efficiency by just avoiding data movements. And this is true for the complex multi-tier systems which we have in general purpose computing, but is also true for simple, very efficient computing architectures which we may have at the edge. Actually, compute memories have been proposed into many different flavors regarding the integration in the memory stack, from registers to main memory, and also some solution which tries to do computing in storage. The technology which is employed, SRAM, DRAM, resistive RAMs, the domain in which the computation takes place, and the integration, either inside the memory or near the memory units. So I will use the name compute memories as a catch-all phrase for both in and near memory computing, and then specify what I'm talking about depending on the different solutions. Now, you can basically pick one of each of these 4, and you will have something which has been proposed in the state of the art. And this is the big zoo of compute memory designs. In particular, Bitline computing is something which targets main memory, even if there are solutions which instead reside in the cache and use very similar principles. They operate in the digital domain. They do computation mainly in memory or in a combination between in and near memory, and they mainly target static RAMs. So why that? Well, first of all, static RAM is kind of a mature technology and is usually the technology of choice when we're talking about main memory for edge devices, and it also can be integrated without any digital to analog conversion. So here is a design. It's kind of an extreme case, and the authors of this design, they claim that their memories were very, very compact. But then, if you look at the layout, much of the space is actually not taken by the memories, but is taken by the peripheral circuit, especially digital to analog and analog to digital converter. As a disclaimer, in those papers, they were not trying to minimize those areas. So yes, something can be done, and we will see something about it even for analog solutions. On the other side, when we're using digital technologies, we can rely on very established tool flows, either full custom or semi-custom design, which is very much easier to manage with respect to digital solution in which noise is very much a problem. And there is a lot of literature in which strategies are proposed to limit the noise when we're talking about analog in-memory computing design. So for all these reasons, SRAM-based digital compute memories are a very attractive solution. So what is all this Bitline computing about? The main trick in Bitline computing is that we have an SRAM array and we activate two memory words at the same time. In this example, we have just two bit cells. You have to imagine that those two, they belong to different words. And when accessing them, bit lines are pre-charged, and then they may discharge according to given path towards ground. Normally, if we have only one bit cell which is activated, we have that one bit line contains the value stored in the cell, the other bit line contains the negated value. But if we activate two cells at the same time, then there are two different discharging paths which the charge on the bit line may take in order to reach ground. If we do the truth table of this situation, we have at the output, we have the AND and the NOR of the bits on the bit line. If you want to have a mnemonics, these are the Boolean functions with 3 letters. So no NAND, no OR, AND and OR. So, and this is something which we can leverage in order to do some computation, because doing the AND and the NOR may not seem much, but it's a basis in which we are kind of mixing the content of two words, and then from there we can proceed to do something more complicated and hopefully useful. So first of all, a few words about the memory organization. For layout reasons, usually we have that SRAMs are organized in local groups, and each local group has this local bit line, and these local bit lines then communicate with the global bit line, which for our purpose is a very interesting arrangement, because we can propagate the value of the bit cell to the local bit line and use the value on the local bit line to do the mixing in between two words in two different local groups without interfering with the context of the bit cell. So basically we're using the capacity of the local bit line to separate the content of the bit cell with the memory computation that we want to do, and we don't accidentally overwrite what we are reading. The second thing to notice is that for layout reason again, usually multiple words are stored in a bit interleaved way. So this would be the most significant bit of the first word, this will be the most significant bit of the second word, and so on and so forth. This is called way interleaving. Now, what more can we do in addition to and or? Well, we can do some negation, and this can be done at the local group periphery, where there are some operational amplifier inside, and these buffers can be used to separate on one side the local bitline from the global bitline, and on the other, we can put some cross connection in order to negate the value which we read at the level of the local group itself. Second thing which we can do is that we can do some shifting. How to do that? Well, we take the bit lines of one bit column and we just connect it also to the next bit column, so that at this level we may choose if we want to read the bit pertaining to this bit column or to the previous one. Of course, this can scale up, so we can just connect 2-bit columns, 3-bit columns, 4-bit columns, but it has a price to pay, and just using a handful of embedded shields in this way can give us basically all the performance that we need for our application, and bear with me, this will be more clear in few slides. Finally, what we can do is to do some addition. In order to do that, we have to exit the array of local groups and go at the memory array periphery, and there with just few logic gates, we can implement a ripple carry adder. This is 1-bit column, so this is only 1 bit. The NOR and the AND come in. We use 1, 2, 3, 4 different gates, and we generate the carry out and the sum bit. Of course, this can be chained for the different bit columns, and even more interestingly, we can break this carry chain if we want to have some data level parallelism. So if we make this connection programmable, and this is, for example, 16 bits, we can use that as 2 fields of 8 bits, and this will be independent, and this can foreshadow something about quantization. As a side note, yes, we can do that, but it's also a little bit costly in terms of hardware, so we don't want to overdo that. So we don't want to make any connection in the carry chain configurable. So, how does that work? Well, it works pretty well. This is a design which my group, in particular, Alexandre Levis, did in 28 nanometers technology. This is the layout. It worked up until 2.2 gigahertz, which it's maybe even an overkill in the edge domain. 640 bytes for each subarray. If I remember it well, this was 4 different subarray, and we also simulated at the post place and route level how this behaved with 4, 32, and 128 subarrays. So the area which we have at the end is something which is still dominated by the memory itself, which is what we want. So we want to have a compute memory, but we want this to be at least a semi-decent memory in case the compute capabilities are not needed and the actual memory array is used just to store data. On the other side, the in-memory operations were pretty cheap, so on average, these were in the same ballpark as the read and write operation which we had. And again, this is just for a 640 bytes per subarray, so these area numbers are actually pretty interesting. And here, if you want to know what happiness looks like, this is what happiness looks like, because this is the first test of the taped out chip, and it actually worked. In this experiment, my colleagues were putting 2 input values in the scan chain used to test the device and getting back the output values and looking at that in an oscilloscope, and yeah, everything worked and they were very happy about it. This macro was integrated in something called Hippocrates. I will talk more about this board in particular in, I think, 30 minutes from now. So this is the hardware. What can we do with it? I mean, we can do shifts, bitwise negations, and we can do additions. Doesn't seem like much, but these are actually the 3 operations which we need in order to implement fixed point signed multiplication in a bit serial way. And yeah, multiplications, max, dot product, linear algebra, machine learning, yeah, you can see a progression there. So what is the trick? The trick is that we want numbers to be in choose complement. Does everybody know what choose complement is? So in choose complement, the first most significant digit can be 0, 1. If it's 0, this is intended to multiply by a power of 2, which is positive. If it is 1, it is meant to be multiplied by a power of 2 with a minus sign on the front, and all the other numbers are exactly like you would have in an unsigned representation. But this is choose complement in fixed point format in between -1 and 1. So the most significant bit is actually 2 to the power of 0, and all the others are fractional ones. What is the catch? The catch is that if you multiply 2 numbers in between -1 and 1, your result is guaranteed to be in between -1 and 1. So while doing a multiplication, we'll never have an overflow error. We may have a quantization error, a truncation error, but we will not have an overflow error. Actually, if you don't believe me, this is the step-by-step process of multiplying 2 numbers. And you can imagine that this green number is stored in the memory, and this red number here is processed bit by bit by different in-memory operations. So this number is here put into the column. We need a temporary storage to do the accumulation, and at each step of our accumulation, we discard the least significant bit, which is not a problem because we only do truncation errors, we don't do overflow errors, and we proceed to do shifts and add. Just in the last step, we also have to do some negation because being the number in choose complement, the most significant bit is intended to be negative. Now, what I have done now is to substitute something which is a multiplication, which I could have done with the combinatorial multiplier in 1 clock cycle, with a serial machinery using adds and shifts, which may take multiple clock cycles. And one question that you may rightly have is, what's the point? You just made everything terribly slower. Well, there is a point if we have to do many multiplications between one operand, which always stays the same, and many different operands, and if our bit width, at least of this operand, which is always the same, is small. How do we do that? We put the operands which changes inside the memory, and the operand which has to multiply many different numbers, stringed bit by bit from the outside by doing the shift and adds. So we call these memories in-memory operands for obvious reasons, and the bit-streamed operand, the broadcasted operand. Where is this the case? It is the case for convolutional layers. So if we have a convolution, then we can take our input activations, just slice them put every slice inside the subarray, and then broadcast the weights, which are reused across the different slices of the inputs. Just as a side note, you cannot do these slices on a plane-by-plane basis, otherwise you would destroy your data reuse. You really want to do the slicing in the Z direction so that you can broadcast the same weight to multiple subarrays and do your multiplications all at once. Things are a little bit more tricky for fully connected layers, because in fully connected layers, we use every weight exactly once. We never reuse a weight to multiply different operands. So what we did in this case was just to switch the role of activation and weights when we're talking about broadcasted operands and in-memory operands. We put inside the memories the weights, and we broadcasted bit by bit the activations. Hopefully you remember this. So now we have something which is good in processing heterogeneously quantized neural networks. Why so? Because if we stream bit by bit, then our broadcasted operand can be absolutely any bit width. There is no restriction into that. And our in-memory operands can also have some different level of quantizations depending on how configurable I make the carry chain into my ripple carry adder inside the computing unit. So I can take my machine learning model, select a layer, decide that I want to quantize it to less bits, doing some fine-tuning, do some retraining, accuracy evaluation, etc. Exactly like we did yesterday. This is how this is embodied for Bitline computing operations. So we started from a baseline implementation where everything was 8 bits. Why so? Because at that level, for all of our benchmarks, there was no difference with respect to a floating point implementation. Then we did the per layer quantization of the broadcasted operands, and at this point we could have that the weights in convolutional layers and the activation in fully collected layers could be basically any integer number. And as we did so, some of the filters in the CNN, they became identically zeros. Because if you just have an handful of bits, you have more and more probability that the values being stored become zero, because everything which is close to zero becomes zero. So we could get rid of some of the filters because they were basically zero. And finally, we also quantized the in-memory operands either to 8 or 16 bits. So how does this work? Well, here on the black line, we have homogeneous quantization. So everything is 8 bits, 7 bits, 6 bits, and blah. And here on the blue and the green line, we have what is the energy accuracy trade-off for different levels of accuracy drop, 1% and 5%. So AlexNet, Cypher 100, what we obtain is that even for a 1% accuracy drop, we could reduce the energy by 60% by performing all multiplications inside our compute memories. And yeah, same thing for a bunch of different networks. We had very similar results. Do you have any questions before I move on? Yes, please.
What is the percentage of memory usage for the PCB usage in your
Can you speak a little bit louder?
What is the percentage of CPU usage and memory usage in your use case?
Okay, so the question is, what is the percentage of CPU versus compute memory use? So here everything is done in the compute memories, and we are just evaluating that, with the catch that we are just evaluating the multiplications which are required by the benchmarks. So we are not evaluating everything which is not multiplication, and we are not evaluating everything which is not fully connected in convolutional layers, and we are not evaluating the overhead which is required to scale values in between -1 and 1. I will address most of this, if not all, in the next few slides.
So how optimal about the uniform quantum lines? Because for different layer, they has different sensitivity to accuracy. For example, for the weights, linear layer, maybe it's less sensitivity to the quantization.
So the question was about this sensitivity analysis block, which I glossed over many times already. So what we did in some of these works was to take the network after the initial quantization, train every layer iteratively at a different quantization, and measure what was the impact. So in order to order the different layers. And this was our initial idea about that. It turned out that actually, by ordering the layers just by required in-memory operations, so required shifts, adds, and negation, you can have an ordering which works quite well and doesn't require any profiling or any accuracy evaluation at all. So for this work, we actually used what was the impact on quality of service. For the next result that I'm going to show you, we just ordered layers in terms of how big they were. And this ordering is kind of dynamic, because as we are optimizing more and more, its contribution will be less, so we will start looking at other layers which become the bottleneck. Other questions? Cool. So, I said that if we multiply two numbers that are between -1 and 1, then the result is guaranteed to be between -1 and 1. Unfortunately, what we would really like to do is a dot product, because matrix vector multiplications, matrix multiplications, basically everything in linear algebra can be interpreted as a sequence of dot products. And in dot products, we have this nasty sum. If we add two numbers which are in between -1 and 1, we have no guarantee that the result will be between -1 and 1. So we may have an overflow, which is bad for compute memories, because the word size is fixed. It's not something which we can dynamically change at any time. On the other side of the coin, the number of bits which we need only grows logarithmically with the numbers of elements which we add together. If we have to add together 1024 numbers, then we only need 10 more bits to be guaranteed not to have overflow. So in practice, when we're doing convolutionals of fully connected layers, what we're doing is to add together the multiplication of a bunch of activations and weights, and this access sequentially in memory different words which then we multiply and add together. So by looking at the memory size, at the subarray size, we know how many bits we need, and in practice, for the designs which we implemented, by just using two registers as accumulation registers, we could host this type of operations. Let's take a look of what we designed, and this is a little bit complicated, so I will go step by step. If you have any questions, please stop me anytime. So we have our memory and we have our logic at the periphery, and now I'm taking a one-column bit slice of that, okay? So as before, we have the capability to do negation by just cross-connecting the bit lines, and we had the capability to do shifts by connecting the bit lines of a bit column to the bit lines of the next column. What we need to do is to have 3 different registers. One register stores the product, and this is exactly like before. And then when we finished computing the product between an in-memory operand and a broadcasted operand, we operate between this value and the value which is stored in the accumulator. This accumulator is initialized by 0, and this is where we store the result of our dot product. If we detect that there is an overflow in this register, then we do an operation with a set of constants which either increase or decrease the value of this MAC-H register. I'm sorry. So by doing that, what we're doing is that we are introducing the overhead of a further operation, but this operation is only done when we're doing the accumulation. So, and this is a 1 clock cycle operation. And we have introduced the overhead of having these 2 further registers, one storing the least significant bit and one storing the most significant bits of our operation. You may ask, why do you need 2 registers and you don't use a larger one? Well, for layout considerations, we only have the space for 1 word in the horizontal layout of our compute memory. We cannot cram 2 different words. Questions about that? So why do we need all these different combinations of constants? -1, -1, +1, +1, +1, -1, etc. So if we decide to store 2 different words in 2 different bit fields in our in-memory operands, so we have a memory width of 16 bits and we store 2 values of 8 bits, then we have to be able to increase one part of this counter and decrease the other, to decrease one part and increase the other, and so on and so forth. And by using the byte enables, we can avoid storing combinations with 0. If we don't have to increase or decrease, which is actually the most common case in which we don't have overflow, then we just use the byte enables to say, do nothing on a given bit field. Interestingly enough, all what I explained you is based on Bitline computing, but you can implement exactly the same functionality by using standard logic design based on digital operators, and by using, instead of full custom design, just standard digital design with standard cell libraries. So this is done in Virtuoso. This is just a bunch of Verilog. So we also did that, and we compared what were the performance of a full custom design with respect to a digital design. But before that, let me take a step back, say, okay, what is the system perspective of this? So what we are assuming is that we have some input activations and some weights. The weights can be statically scaled between -1 and 1, no problems at all. Input activations have to be scaled at runtime between -1 and 1, because we don't know their value beforehand. Then we can go into our compute memory, do all of our tricks. The result will not be between -1 and 1, so we have to do some post-scaling, scaling back, and we can proceed with the next layer. As of today, all this part is not in the scope of what I'm going to present. I hope to see you in the near future, and there I will present also some ideas on how to implement this part. What I can say is that in order to scale the data according to a maximum, you just need to do two linear passes on the data. One to decide what the maximum is, and the other one to do the scaling. While convolutions are fully connected at a much higher computational complexity, so these two operations are actually not critical for the runtime. So, from a circuit perspective, how does it work? We implemented that with multiple 2 kilobyte subarrays, 28 nanometer technology, 6 transistor SRAM. We achieved the same operating frequency. We supported in-memory operands with either 16 bits or 2 times 8 bits. And we can see that both for the Bitline computing full custom design and for the near memory computing fully digital design, the area of operation is rather small. So here we were attaching all the logic which I explained to you to a 2 kilobyte subarray, which I hope you agree is a rather small memory. But even with that, the memory itself still occupied 80% of the area. As for the energy, again, we have that the in-memory operations are as efficient as normal read and write operations toward the memory. So we are in a good place with respect to that. And that the in-memory computing, so the Bitline computing full custom design, is 16% more efficient than the near memory computing. So here it's really a choice on how much effort you want to spend on to design. Do you want just to write some VHDL or Verilog? Fine. What you pay is basically 16% in terms of energy and something very similar in terms of area efficiency. Just as a ballpark, this was an effort of 1 to 2 months for a very smart PhD student, Marco Rios, and this he implemented in less than a week. As for the runtime characteristics, so first of all, how does this type of structure scale? I told you that all this only makes sense if we can have a lot of subarrays working in parallel so that we can broadcast one operand bit by bit. So for a practical case, AlexNet is not the bigger network that you can think about, but up until 128 subarrays, it scales quite well. So we can harness the application parallelism into the hardware. Then, all of our little game of having overflow registers, etc., it's something which proves to be pretty effective. Here I'm comparing with just scaling everything. So even if we have a 16-bit words, we just scale inputs to 8 bits in order not to have overflow at any time. And in this case, what we pay is in terms of performance, because half of our memory is just used for sign extensions for the input. The alternative would be to use saturation, so we just use all the bits in the word for the inputs, and if the output saturates, then it saturates. So saturation just doesn't work. Our accuracy becomes basically useless. While overscaling to few bits the operand has an impact on the performance, because then we cannot do as aggressive quantization as we did before. Now, this is the main take-home message from the Bitline computing perspective, but it turns out that with Bitline computing you can play a few other tricks. So let me show you which other tricks you can do. One thing you can do is memory protection. So we have spoken about increasing the robustness of applications, and in particular, ensembling. If you remember, we can take a network and up until a point, just reduce the network size replicate the network so many times so that we don't increase the network size in total, but we obtain something which is more robust. And this will buy you some robustness, but up until a certain threshold. If our bit error rates become bigger and bigger, only algorithmic level solutions will only help you so far. So what you can do instead is to embed error detection and mitigation inside Bitline computing memories. I'm not talking about error correction, I'm talking about error mitigation. And we will see how this, in the case of machine learning, can be done very effectively. So what we have to do is to include a parity bit, and this is an overhead which is basically unavoidable, and to complicate a little bit the Bitline computing unit. What's the main idea? So if you need to compute or to check a parity, you have to do the XOR in between the values that you are reading. Now, if you're accessing two operands at the same time, then you would have to do the XOR of all the bits that you're reading in both words. But it turns out that our Bitline computing logic already mixes the two words a little bit. So by doing the NOR between the Bitline computing and the Bitline computing negated, here I'm missing a negated, I'm sorry. Then you're doing the XOR between Q0 and Q1. And this simplifies our hardware quite a lot because we don't have to have two separate XOR trees. We can use the same one with just a little bit of additional logic. Second trick derives from the fact that the expected value of arithmetic operations in machine learning is 0. So if we detect an error in what we're doing, the best guess we can do is to put the output of that operation to 0. And this is application specific. In other cases, things may change, but in here is kind of a reasonable assumption that if you have no idea what's the output of an operation, the output is 0. This is how the hardware looks. And this is the third trick which we employed, which is that we can use the same XOR tree twice. So we can take the operand or the operands we have to use in order to do a Bitline computing operation. We traverse our XOR tree to see if there is an error or not. And then, if there is an error, we can just clear the output to 0. If there is no error, we can, in parallel, compute the Bitline computing operation, compute the parity bit appropriately, and store it back. The only part which we have in terms of timing overhead is actually the parity generation or the error mitigation. Error mitigation means putting everything to 0. Parity generation means generating the parity bit and storing it back. And across all of our experiments, this extra overhead was never more than 10% of the entire clock period at 1 gigahertz, if I remember it well. So, in order to evaluate this methodology, we needed to define what are the benchmarks, what are the architectural parameters, so how big is our compute memory, and what is the trade-off between energy and error rates. For this part, so the relation between voltage supply and error rate for a given SRAM subarray, we shamelessly took data from the state of the art. So we thank Daniele Bortolotti for publishing this. Nevertheless, we obtained results which are pretty nice. So again, This is the black line, and it is no parity at all. It just fails if the voltage goes around 650 millivolts, because the bit error rate is so big that the results are basically useless. In our case, we could scale much more. So at 650 millivolts, we still had a pretty decent quality of service, and we had an energy gain of 51%. And this includes the overhead of computing, of checking parities, of storing those parity bits, and so on and so forth. So there is an overhead, but the gain that we have by being able to scale the voltage further down more than compensates the overhead that we have in terms of energy. Questions? Okay. Further trick. So I have briefly mentioned resistive RAMs in one of my previous slides. These are non-volatile memories which are characterized by a pretty higher write energy, but by no leakage, because they retain their value even when they're powered off. In addition, they are much smaller than SRAM bit cells. Interestingly, RAM can be co-integrated with SRAMs by using the same technological processes. So again, Marco Rios came up with this interesting structure in which we have, for the same area, either one SRAM bit cell, all 4 RRAM bit cells, and these are pitch matched at the level of the layout. We plan to use this type of hybrid solution in order to be able to store values which change very little, weights, in RRAMs, and values which instead change very often, activation, in SRAM. I will stop here with some characterization at the hardware level for this type of hybrid memory, but you can expect much more in the future, because this is, I think, a very interesting type of structure which marries very well with the application characteristics of machine learning applications.
So what is the simulator in this one?
What is the? Sorry?
Simulator.
The simulator. This is integrated at the place and route level, and we took data from the state of the art to understand how big the layout of the memory cells could be done. And we also took values from the state of the art to characterize the access energy to the different RAM cells. Yes?
Do you use the same local periphery for both technologies?
You need a little bit more, because the SRAM cell doesn't need any reference, because it already has 2 outputs, 1 straight and 1 negated. In the case of RRAMs, you need a voltage level from that you have to compare to in order to understand if you're storing a 0 or a 1. So this is one reference voltage that you have to provide for the entire subarray. It has a little bit of overhead, but not too much. Actually, the trick is that you can connect 2 different RRAM cells at the bit line and to the bit line negated. This is how you can have a lot of density. Other questions? Okay. So, Bitline computing allows to have any bit width for the broadcasted operand and few bit widths for the in-memory operands. Here is a solution which instead allows you to have any bit width for the broadcasted operand and any bit width also for the in-memory operand. And it's called software-defined SIMD. SIMD, of course, stands for single instruction, multiple data, and it means that multiple subwords are encoded into a word. This is very interesting because here are many examples of different CNNs, and each tuple of columns represent a layer. Blue are the activations and orange are the weights, and we can actually map something like this in which change very widely the bit width of weights and activations in different layers, and these implementations are 1% accuracy loss with respect to floating point. The bit width range from 0 to, in very seldom case, 16. Now, this is something which you can possibly do also with traditional SIMD, but at a very high cost. So in practice, in traditional SIMD, you are limited in terms of supported SIMD modes, but you can do your multiplications in parallel. With software-defined SIMD, there is no limitation on the bit width of the subwords, but our multiplication is serial. So again, so SIMD, similarly to the case of Bitline computing, is efficient when we have data parallelism, small bit width, and heterogeneous quantization. How does that work? So the main care of soft SIMD is that whatever happens in the subword should not influence another subword. Whatever happens in Vegas stays in Vegas. Whatever happens in a subword stays in a subword. And this can be done by using garbits, which are reserved locations in our words, which separate the different subwords. How are they used? So if we have to do an addition, then this would be our garbits, and we have to ensure that the carry-in of a subword is always 0 in order to not corrupt it. So we put the garbits to 0. Whatever happens in the subword cannot make that carry-in to become 1. R for subtraction is the opposite. When we do a subtraction, we want the carry-in to be 1, because in choose complement, we have to negate one operand and add 1. So we put the garbits to 1, and this will ensure that no matter what happens to the previous subword, the carry-in to the next subword will be 1. This is something which is very similar to what we did for the Bitline computing case. Again, this is a multiplication in choose complement among one operand, which is stringed almost bit by bit, actually bit groups by bit groups, more on that later, and another operand which is instead composed by 2 different subwords. We do our operations in terms of shift and adds, and we have only truncation errors, but we don't have overflow errors. So what about this CSD coding? So CSD is not something new. It's been around, as far as I know, for at least 30 years. And it's an encoding that instead of using 2 symbols, 0 and 1, uses symbols, 0, 1, minus 1. If we do that, then we can maximize the number of zeros which we use to represent our value. If we have a lot of zeros, then instead of doing shift add, we can do multiple shifts add. Plus, if we have a minus, we have to do a negation, which is something which we know how to do very effectively in hardware. So in order to do this multiplication, I just need 1, 2, 3, 4 operations, so 4 clock cycles. This is how the SoftSIMD pipeline looks like. It has an arithmetic unit which supports exactly the operations which we have seen in the previous slide, and a data repacking unit, which is basically a crossbars, which allows us to transition from one bit width to another. If inside this data packing unit, we may have the input, which is a given bit width, and an output, which, for example, has a bigger bit width. If you have paid attention, of course, we need this when doing machine learning applications, if we have to do some additions in between numbers in order to compute dot products. The PhD student of the Embedded System Laboratory in charge of this work is Pembo Yu, and he actually implemented that down to the place and route level. And it turns out that by doing this design, we can support efficiently machine learning applications in a very small area with respect to using a SIMD multiplier, even if our source SIMD implementation supports all these subword sizes, while the baseline, which is a combinatorial SIMD multiplier, only supports those. We just stopped there because supporting even more SIMD modes for the baseline would just make the area explode and would be a very much a reasonable design. So smaller is often more energy efficient, and this is also the case here. What we did was to map all the multiplication and addition operations which are required for these networks, for these CNNs inside such an architecture, and we measured how much energy was needed, and our design was way more efficient than using a traditional SIMD multiplier. As a disclaimer, here we measured only the energy of the data path, not the energy of the memory itself. This is ongoing work, and I hope to have numbers about that next time we meet. Nevertheless, computation-wise, this seems to be a rather nice solution if we're looking at energy. If we're looking at raw performance instead, we do have a slowdown because instead of doing operations combinatorially in one clock cycle, we are forced to do that in groups of bits. Now, this is not that bad as it may seem, because if you have a smaller accelerator, you may have multiple copies of that. So area and performance are not completely disjoint from each other, because you can have more of these guys for the price of a few of these guys. Nevertheless, having something which is lower is not always nice. So we look into a way of making our architecture faster, and in particular as something which we term dynamic bit width frequency scaling. I guess that most of you are aware of dynamic voltage frequency scaling, but we are talking about dynamic bit width frequency scaling. The catch is that if we have a ripple carry adder, which is what we have in our implementation, then the smaller the bit width, the smaller the critical path is. And since different subwords are separated by garbage, this is kind of an effective critical path. It's not the critical path which is reported by design tools, but is the critical path which is exercised in practice given a subword design. So in this case, we could obtain something which not only is smaller, not only is more energy efficient, but now it becomes even faster with respect to an equivalent, so hard SIMD implementation with a combinatorial multiplier, because we could scale up the working frequency. This is all I had to say today for the accelerator-based solution. And now I would like to start talking about how to compute part 2, so open source hardware and system simulation frameworks. So I go back to this slide because it is something which I would really like you to remember, the tug of war between edge applications and edge systems. This is a complex challenge to tackle. And in order to do that, we need tools, and we need tools which allows us to inspect solutions from a whole application, whole system perspective at different levels of abstraction. Two particular levels of abstraction which are of interest are open hardware frameworks and system simulation frameworks. What is the difference? The main difference is that an open hardware framework allows a path to fabrication, so you can design a system, lay it out, either download it to an FPGA or go for fabrication and inspect it working, let's say, for real, while in system simulation frameworks, you abstract away the implementation and you just define modules which define the behavior of different system components. Of course, there is a different level of abstraction in between the two, and also the level of system complexity which can be managed. Am I making someone cry? I hope it's not me, really. So, the level of system complexity which can be managed at the two levels is different. Let's start with open hardware frameworks today, and then we see how much time we will have. So we're living in interesting times from this perspective, because right now there are open source solutions across all the stack in order to implement your edge AI system. You have a way to specify models. You have a way to execute models in processor with a given instruction set. You have a bunch of cores and peripherals and memory macros which are available from multiple sources. You have tools to perform synthesis and place and route down to GDS II, and even some technologies which may be positively ancient but are freely available. Actually, something which is not mentioned in this slide is that HiPEAC has recently opened a quite advanced technology node which can be requested for free and used for non-commercial purposes. And there are a number of projects which are growing regarding open hardware, and this growth of open hardware initiatives kind of mirror what has happened to open software something like 10 years ago. I guess that many of you have at least heard of the Pulp project. It has been around for quite a while and is mainly focusing on ultra-parallel, ultra-low power systems. There are other initiatives like Chipyard or ESP in which they try to provide menus of different components when designers can mix and match and enrich. And then OpenTitan is more focused on security aspects and provide security primitives. The CHIPS Alliance provides free ADA tools, but also IPs and generators for different type of macros. OpenRoad and FreePDKs provide tool sets in order to develop chips. So there is an ecosystem and it's growing very, very fast. This is our contribution to this ecosystem, and it's called X-HEEP. Anyone has heard of X-HEEP before? Okay, cool. So what is X-HEEP? X-HEEP is a set of core modules which allows you to investigate your fancy new accelerator or your fancy new hardware-software solution by providing all the boring stuff. So, what is inside this orange box is provided by the X-HEEP environment, and it just works, is integrated, provides software, hardware, and everything. So that you can provide extensions, accelerators, peripherals, and so on and so forth. It is available now at this GitHub repository, and it comprises different components, tutorials, and also different targets, as we will see in a second. So the main idea is that we want to provide everything which you may need in order to start experimenting with your fancy accelerator, and we want to make it easily configurable so you can swap in and out different components, different peripherals, different interconnect styles. Moreover, we don't want to reinvent the wheel, so whatever we could reuse from other sources in order to realize the X-HEEP framework, we just did. So we took the CPU from the Open Hardware group, the bus from the PULP project, the debug unit also from PULP, a bunch of peripherals from OpenTitan, and so on and so forth. We tried to integrate those and to make this type of integration easy for the architectural developer. The idea being that the effort should not be put here, but to whatever you want to integrate. So these are examples of configurabilities. So these are peripherals which may or may not be part of an X-HEEP system. There are deep support for different power domains, from CPU, memory, and so on and so forth. There are different styles of interconnect depending on how much performance you want to have. You may have a single bus which is arbitrated among different masters and slaves, or you have a fully connected cross bus, or anything in between. Of course, we also provide a software developing environment. Actually, we provide two of them, and the RISC-V compiler is a mature technology so that you can start using X-HEEP now. From our side, what we provide is hierarchical and integrated hardware abstraction layers for all the peripherals that you may want to integrate to its programmability. Yes?
For the workflow you simulate in your framework, do you have to write for each workload a support package, or it's generic enough to support multiple workloads?
So the question was, do you need to write a support package? So you can rely for that on the hardware abstraction layer. Depending on which peripherals are available in your system, then you will have different ways to interface to that. Of course, the interface to your own accelerator is something that, yeah, you have to provide. Yes?
And do you allow in your workflow to make modifications to the RTL of the code, the RISC-V code? Running instructions, for example?
Absolutely yes. So this is why there is a coprocessor interface, but in general, okay. In this coprocessor interface, you can add your own instructions, so you can have tightly coupled or loosely coupled accelerators. In general, you can tamper with the system on chip as much as you want, because it's all open source. So all the very low code is available, and you can do whatever you want with it. Other questions? Yes?
Do you also provide scripts for the backend, for the ACID backend flow?
Yes. So do you provide scripts for the ASIC backend flow? The answer is yes, and this goes back to here. So what you can do with X-HEEP. So you can do emulations on FPGAs, and we support natively the pink board, in which on the processor side, we run Beta Linux, and we can use that as a debug unit for your X-HEEP system, which lives into the programmable logic side of the FPGA on the pink board. Or you can have ASIC backends. So, of course, the technology itself is something that you have to provide according to your needs, but there is all the scripts which are used in order to do the synthesis, the place and route, etc., etc. And this is our first tape out of an X-HEEP system. You can see here that there are some known entities, like a CGRA here, some Bitline computing there, and we use that first as an example of how you can make an heterogeneous system on chip, and secondly, to test those components as real ASIC circuitries. So this is the board itself, which embeds the Hippocrates chip, which is here and is our first X-HEEP system on chip. The system on chip itself has 60mm, 865 nanometer TSMC technology. It's a very wide frequency range, from 32 kilohertz to 470 megahertz, and also parallel consumption, which also varies according to the frequency, but anyway stays pretty low. Now we are 2 tape outs coming from Hypnosis and Hypatia in the end of 2024. Each of them will embed a bunch of different accelerators, and we plan to make this very much a vehicle for the exploration of edge architectures, and we welcome contributions from all of you in order to make this kind of a regular stream of tape outs, which we will have out of the system. Actually, it's getting pretty crazy. So we have people looking at POSIT core processors. If you don't know about that, POSIT is a way to represent values using something which is even more flexible than floating point. We have people looking at Cordic accelerators, embedded GPUs. So anybody's taking the GPU course in the morning? So yeah, where they are developing an open hardware GPU called the Vortex. We are very much looking at it and trying to interface a derivative of that inside of our system. Other people are looking at cryptography, and here you can see basically all the play of words you can make on the HEEP moniker: Hippocrates, Hypatia, Hypnosis, Hyperator, Epsilon, RACEHEEP, Phi, HiPi, HiPEAC. Each of these are different projects which either internal in the lab or with external collaborator we are pursuing in this context. And it is getting pretty crowded. This is one of the meetings which we recently had regarding this initiative. And you can get started with X-HEEP by just looking at the documentation. We try to make it as up-to-date as possible, and or downloading our Docker file. Any question about X-HEEP? Okay, so I will just now transition to system simulation frameworks, and I will introduce that briefly, and then tomorrow we will have many examples how system simulation frameworks can help us explore how useful different styles of accelerators are in order to accelerate machine learning applications. So what is a system simulator? Is a tool which allows to specify a parameterized virtual machine. It basically has a configuration script which expresses how we want our system to be, how many processors, which type of processors, what is the cache hierarchy, what is the interconnect, and so on and so forth. And then this virtual machine is spawned, and you can connect to this virtual machine and launch applications on that. The virtual machine is fully featured in the sense that you can run Linux on it or another operating system, and then you can use profiling in order to understand what are the characteristics of an application when running on the system that you specified. Here I will focus on Gen 5, even if alternatives exist, but Gen 5 is by and large the most used system simulation around. Is contributed basically by everyone, so I would be surprised if there is any major company or some major university in our field which does not contribute to Gen 5, and it can either work in full system simulation, so simulating all the hardware software stack, or in syscall emulation, where system calls are just trapped and ignored during simulation. In our lab, we developed a layer on top of Gen 5, which we call Gen 5X, which allows us to do some operations more conveniently. For example, it allows us to drag and drop between the host machine and the virtual simulated one. So we don't have to restart the simulation every time we want to launch a new application or we want to change the data set. And we expanded that with the ways to do architectural extensions. In particular, I will talk about wireless links, scratchpad memories, and various types of accelerators. The simulator itself is validated with respect to real hardware, is available as open source on a GitHub, and if you want to know more about that, on YouTube you can find either a high-level tutorial for Professor Zapater or low-level technical introductions from Joshua Klein. How to do a Gen 5 simulation? You just define what your system looks like. So it should boot a disk image with Ubuntu, and it has a CPU of 1 GHz with one processor, a given L2 cache, a given L1 cache, and a given main memory. This will give all the information which is needed to spawn the virtual machine. Then from your host machine, you connect via Telnet, and whenever you want to start recording stats, use M5 commands from that shell from which you did the telnet, and you, by dumping the statistics, you can inspect them. And those statistics, oh boy, are detailed. If there is an architectural parameter in a system, good chances are that you can find it into the reports. Tomorrow, we will see how to enrich a standard system with accelerators, and we will start by looking at a kind of systolic array which we call TICSAT, and that we gear towards accelerating transformers. I think I can stop here for today. Do you have further questions? Seeing none, so I just wish you a very nice evening and see you at dinner time.